Welcome to month 3 of AOA. This month we will be covering divide and conquer algorithms. In this slide we have an overview of what we will be covering today, so feel free to pause here.
So just briefly, we'll be talking about divide and conquer algorithms, their use cases, many different examples of these algorithms, and at the end, some advantages and disadvantages of using divide and conquer. So the first question is, what is divide and conquer programming? And it really boils down to three key things, which is first, dividing the problem into smaller pieces, and second, solving each smaller part recursively, as in, if they're not small enough to be directly solved yet, you can break them up into more pieces. At the end, you can combine the solutions back up to get your final solution. And it'll make more sense once we get into some examples. The first step is division. So, assuming your main problem is too difficult to be solved in just one step, or you're not sure how to do it, what divide and conquer allows you to do is actually divide the problem into two or more subproblems. So, one easy example is binary search, where it's too difficult to just look at an array and immediately know where the number you're looking for is. So you look in the middle and determine if your desired value is greater than or less than that middle value. Then you split it up into subproblems, which is if it's smaller than, then you take the left half of the array, and if it's bigger than, you'll take the right half of the array. Second step is recursion. In divide and conquer programming, you recursively solve each subproblem. If the subproblem is still too large, you'll have to break it up again into even smaller subproblems. So, going back to the example of binary search, even if you break the array in half, if it's still like 10 or 20 values long, it'll still be too difficult to find the desired value easily. An easy way is to check the midpoint again and further break up the array into smaller pieces until they're of manageable length. The final step is recombination. Now, some algorithms don't actually require recombination. For example, if you're in binary search and you find the index of your desired value, you immediately have your answer, and you have no need to further recombine your solutions back into a full solution. However, if you're trying to do something like sort an array, you will need to recombine these smaller subparts. So, one example is if you sort smaller parts of an array and then must recombine them into a final array that is completely sorted. That's an example of recombination, and you'll see this in many of the algorithms that we'll talk about. So the first example is merge sort. Merge sort breaks an array into smaller individual elements, which are then combined at the very end of the process in order to form the final array. So you can see at the top the arrays of size 8, but that's too difficult to sort for us right now, so we'll break it up into two parts that are both 4 long. And then that's still too difficult, so we'll break those further into 4 pieces that are just 2 long. That allows us to directly compare both values and sort them very easily, which can be done using an if statement. Then you'll take each individually sorted element and put those back into arrays of length 2. Then, looking at two arrays of length 2, you put those in sorted order, first picking the smallest element of both arrays until you have an array of length 4. Then at the very end, you'll put those two arrays together into the final array. And at the right, you can see which parts are division and which parts are the recursive solving. And then at the end, it'll be recombination. The pseudocode for merge sort is to start, declare a array left, right, and mid variable. This is important because you want to decide where you're going to break the array and the limits of what you're trying to sort. Then you'll actually perform the merge function recursively. So if the left is greater than right, you'll return because that means that your array is already of the smallest length. Otherwise, you'll break it up into two different arrays, individually merge sort those two arrays, and then merge both pieces at the end. At the very end, you'll recombine all of them with this final merge function.
Alright, so very similar to merge sort, quicksort is another sorting algorithm that uses divide and conquer programming to increase efficiency. So much like merge sort, first you break the array into smaller subarrays, and this is done with a pivot. The pivot is arbitrarily selected, but it's generally the first or last element of the array. After breaking the array into two subarrays, with one half being elements greater than the pivot and one half being smaller than the pivot, you select a new pivot for each subarray, and you do that over and over again until you've broken down the entire array into subarrays of size 1 or 2. At that point, it's a lot easier to rearrange each element into a sorted order, and then you recombine to get the final sorted array. This slide shows the pseudocode, and it's very similar to a process done in merge sort. So first, we see that you select a pivot. Here, we just select the pivot as the first element of the array. After that, we continue to divide into smaller subarrays by selecting a pivot, and this is done with recursive calls to each of the subarrays. All right, now let's move on to more divide and conquer algorithms. Another one that we can think of is how a factorial function works. So a factorial of an integer is that number times all the numbers smaller than it until you get to 1. So the first step is to take, say, n factorial into n times n minus 1 factorial. You continue to break it down over and over again until you get the base case of n equals 1. When you recombine, you multiply all of these numbers together. For instance, if we take 6 factorial, we know that the base case here is 1, and 1 factorial is 1. So that's our base case. And then we'll divide by expressing 6 factorial as 6 times 5 factorial, 5 factorial as 5 times 4 factorial, so on and so forth. And once we get to 1, we recombine by computing 1 factorial, and then 2 factorial, 3 factorial, so on and so forth. The code is at the right. It's pretty simple. So first we express our base case, which is just 1, and then we express our recursion step. The next algorithm that uses divide and conquer programming is Fibonacci. So if you don't know what Fibonacci is, it's just a sequence where the next term is the sum of the two previous numbers. The sequence goes 1, 1, 2, 3, 5, 8, so on and so forth. We see that 5 is equal to 2 plus 3, 8 is equal to 3 plus 5, 13 is equal to 5 plus 8, so on and so forth. So if we want to determine a certain Fibonacci number, we can divide the number into the sum of the two previous terms. You can see this in the picture at the bottom right. So we see that, like, for instance, the fifth Fibonacci number is expressed as the sum of the fourth and the third. And then the fourth Fibonacci number is equal to the sum of the third and second, so on and so forth. The base case here, so for instance, the 0th and the first Fibonacci numbers are just both 1. Once you get the base case, you recombine by adding up all of these numbers. Now we have the code here. So we express our two base cases. The first and second Fibonacci numbers are both 1, and after that, you break it down into n minus 1 Fibonacci number and the n minus 2 Fibonacci number, and you recombine from there. Now we'll be getting into some algorithms that are a little bit more complicated and require some higher mathematical knowledge, but it will still be pretty intuitive as to how these algorithms increase efficiency. Here, we'll be examining how to optimize the efficiency of large integer multiplication. In elementary and middle school, we've had plenty of practice with multiplying large numbers, but let's say if the size of your number gets to 10 or 20 digits, doing it the conventional way is not only tedious for humans, but also for computers, because multiplying two integers of n digits by each other gets a time efficiency of O of n squared. We could try divide and conquer programming by splitting numbers into chunks randomly and then multiplying it. For instance, if we want to multiply 1,234 by 5,678, we could try multiplying 1,200 by 5,600, 1,200 by 78, 34 by 5,600, and 34 by 78. This gives the exact same result, but at the end, we're still doing 4 computations, which leads to an O of n squared time efficiency. So that method doesn't get us anywhere. But with some algebra and rearrangement of terms, we're able to simplify this into an expression that only requires 3 computations, which leads to a time complexity of O of n log base 2 of 3, or roughly O of n to the power of 1.58. Although this doesn't seem like a big improvement, when n gets really large, and when we're dealing with logarithms, this is quite a large improvement. Next, we're going to be going over matrix multiplication. Once again, the multiplication of integers that we do is very similar to matrix multiplication, but when we're dealing with matrices, multiplying them has a time efficiency of O of n cubed, which means that once matrix sizes get very large, it's tedious and time consuming to compute them. Like we tried before, if we just arbitrarily split these matrices into squares and then recursively compute them, we get the same time complexity of O of n cubed. Strasson's algorithm uses the exact same concept of large integer multiplication by using some algebraic manipulation to rearrange the terms such that we only have to do 7 computations instead of 8 computations. So instead of a time efficiency of O of n cubed, we get something close to O of n to the power of 2.8. Once again, even though this doesn't seem like much, once we get to very, very large matrix sizes, we can see a huge improvement in runtime and efficiency.
So talking about some of the advantages and disadvantages of divide and conquer algorithms, and starting off with the advantages, first is solving complex problems. If you've ever considered simple algorithms for solving a maze or more difficult problems, many will use the divide and conquer approach because it makes harder problems really easy to solve through dividing them into easier problems. Second is parallelism, as you can solve different subproblems at the same time, allowing you to increase efficiency, especially if you have a CPU with multiple cores, allowing you to handle tougher problems in less time. Now, there are also disadvantages to using divide and conquer. Recursion can lead to slow runtimes, as you have to compute different subtasks over and over, and the repeated recursive calls can lead to problems down the line, such as overflow. Another issue is time, as recursion can be slow and resource intensive, and not all problems actually require a divide and conquer approach, which can slow down your algorithm significantly. Third would be efficiency, as dividing the problem into subproblems can lead to solving the same subproblem multiple times, something that could potentially be solved by another approach called dynamic approach, but that's not within the purview of this video. And finally, some of these efficiency issues can be solved with that approach, but that approach requires more advanced techniques that we won't really be going into in this video.
That's all for this month's AOA class. Stay tuned for next month when we will be going over hashing and some of its applications.